Okay, guys, welcome back. Thanks for still being here. Let's go talk about our rates. So that's where we're at. Let's go and talk about that. So we're going to be talking about rates and factors that affect the reaction rates. We'll talk about concentration and rate laws. We'll talk about concentration in time, and then we'll talk about activation energy and the temperature dependence of the rate constant. Okay, so all of that is what we're going to be talking about. Yay, this will be fun. I don't know why there's a question slide there, but okay, fine. So kinetics is the study of the rate of reactions. So when we talk about rates, we're talking about the kinetics. It also provides information on the mechanism of a reaction, and it shows the path by which a reaction occurs. Okay, we don't always know when we're looking at how fast a reaction happens, what the path is from start to finish. We need to do some other types of studies to figure that out, but we will talk about that part in the next lecture. So mechanisms is next time. Kinetics is just about this rate. Well, that's interesting. Well, okay, reaction rate. Well, how do I define a rate? A rate is a change in concentration over a time period. So delta, concentration of A, over delta T. Delta means change in. The brackets mean molar concentration. T represents time. These are for negative for reactants and positive for products. So if I'm, my reaction's going along, I would expect that my reactant would get less and my product would get more. So that's the expectation. So we list this as negative for reactants and positive for products. Okay, so there's a sign difference. And there are a number of different types of rates that I can measure. And we may get asked for some or all of these depending on what we're doing. Now, an average rate is the rate of change over a fixed time period. Okay, so any particular period of time, but it's a change that happens over that time period. An instantaneous rate is measured as the slope of the line at that particular time point, and I'll show you this in a few minutes. We also have a very specific instantaneous rate, which is called the initial rate, which is the one that we measure at time 0 for this particular reaction. Okay, so those are some of the rates that we talk about. Let's see, questions, comments, problems on those. Understand if you don't know exactly what we're talking about, we'll talk about that in a few minutes, okay? All right, before we get to that, we need to talk a little theory. So, collisions happen through a process called the kinetic molecular theory of gases. Is this perfect? No, absolutely not. But it was one of the first approximations for how reactions occur. We talk about them mostly in the gas phase because in the gas phase things move a lot faster, and so we have a lot more information about how these things are connected to each other. So gas is composed of molecules that are separated by distances bigger than their dimensions. We know that. There's a lot of empty space in a gas. Gases are in constant motion in random directions, and they often collide with each other, which is how we measure the pressure of that gas. Okay? Gas molecules are not attracted to or repulsed by other gas molecules. Now, this is an assumption that we make, that when these two things hit, it's a completely elastic reaction. So they hit, nothing happens. So they just, it doesn't change anything. There's no transfer of energy, none of that. That's not really true, but that's an assumption that we've made. The kinetic energy of the gas particles is directly proportional to the temperature of the gas. And that is definitely true. That is exactly what we're talking about when we talk about temperature. So chemical reactions are the result of collisions of molecules. And in your head, at least in my head, let me speak from my head, this makes total sense to me because I can't have a reaction unless I collide with something. So I have to at least physically meet that thing for something to happen. So I can't rearrange my bonds just because there's that dude over there. That's not how that's going to work. We have to be in the same space, okay? So anything that means more collisions means more reactants turn into products. So more collisions come from greater motion. Temperature is a measure of the motion of the molecules. So higher temperature means higher motion. There is a temperature dependence for reactions to occur. Not all reactions are more favorable at higher temperatures. There are a few more factors involved which we haven't really talked about yet. Okay, don't worry, we'll get there. But that's not the only thing that we need to consider. Okay, and just because we need to move, it's better for us to move more in order to be able to do a reaction, that does not mean that all of them have a greater rate at a higher temperature. Okay, well, that was fun. Oh, come on, give me a new slide. Well, that's great. I said that I need to collide with something else to make a product. So chemical reactions are the result of the collision of molecules. But it's not just related to that collision, okay? I have to have more than that. So I can run into somebody in a hallway and nothing happens. But I could run into somebody else in a hallway and something happens. We all know that there are differences in that. Our interactions with other people, molecules are sort of like that. What really needs to happen is that we need to have the correct orientation. So the two parts of the molecules that are going to be going through the changes need to be the ones that hit. So if I don't hit in the correct location, the right side where it needs to physically be, then that reaction is not going to occur. So it's not just a consideration of them hitting each other. They have to hit each other, and they have to be in the correct orientation. Okay? And not all collisions have sufficient energy to result in a reaction. There is a minimum energy that is required for a reaction to take place. And it depends on what the pathway is, what that energy looks like. So some things go very easily, some things don't, and that has a lot to do with that. That activation, it's called an activation energy, but that minimum energy requirement is usually higher than where we start. It almost always is above the initial energy, and that's called an activation energy. Okay? And we form an activated complex, also known as a transition state, when the collisions occur with sufficient energy. So sufficient energy, correct orientation, they come together, and for a brief second, there's this weird molecule that's not exactly reactant, that's not exactly product, it's something in between. And that is called the transition state. Transition state is a temporary species. It is not something that we can go plunk out of the air and look at and measure. That's not what we can't do that. All right. There are ways that we can study it, but it's not easy. So that's our transition state, and that happens at the highest energy point. Okay, awesome. What else? Well, let's talk about potential energy, because I said that there was a minimum energy that needed to occur for this to happen. You're looking at two potential energy diagrams. And I know we haven't seen these yet. We haven't talked about this part. So potential energy is typically related to something called thermodynamics, which we will talk about for exam 3. But we need to be able to talk about parts of it to be able to talk about this. So EA is the activation energy. EA is the difference between where I start, this A plus B energy, and the transition state. So that gap represents EA. Now that can be any size, okay? So this one is fairly small. Over here, it's a lot bigger, okay? Now the other thing that you'll note is that in A, we start medium and end low. So my potential energy as I come out of this is lower than it was, all right? The other one, in B, the potential energy when I come out of this is higher than it was, all right? We talk about these in two different terms. So one is called an exothermic reaction, okay? The other one is called an endothermic reaction. Now, an exothermic reaction means that heat is released during the reaction. So the reason that the energy is so low is because that heat came off. It's a product, okay? Endothermic means that heat is required to make that reaction proceed, okay? So the fact that we're talking about going up in energy means that I have to take that energy in. And of course, I need that activation energy to be enough to make this happen. But I'm not going to give any off at the end, okay? So I'm going to have to take it all in to make this work. And that's an endothermic reaction. So remember that the equilibrium will shift in response to adding or removing a product or a reactant. Since heat is either taken in, a reactant, or given off, a product, then we will see shifts in the equilibrium due to the change in heat. So remember, we talked about equilibrium having a temperature dependence. This is what we were talking about. This is endothermic, exothermic. And again, we'll come back to that when we get to that for exam 3, okay? But we need to be able to talk about EA and what that EA is and how big that EA is, because that energy is required for us to be able to get from our reactants to products. Okay, so some practice for you. After we look at each of these images, what I would like is to see what is the activation energy and what is the energy of the activation complex. Label the heat of the reaction, the activation energy, and the energy of the activated complex. Okay, fine. Let's start at the beginning. The heat of reaction is the difference between my reactants and my products. So here we're talking about 50 joules, because this is 100 kilojoules. 100 kilojoules, this is 50 kilojoules. So that difference is that 100 kilojoules minus the 50 kilojoules, and that's equal to 50 kilojoules that we see right there. 50 kilojoules. Okay. When we talk about, so that's the heat of reaction. And I'm going to write that RXN because I'm too lazy, too whatever to write the whole thing. Now the activation energy is the difference between this starting and this point right here. So that activation energy is EA. Okay, so that's my activation energy. How much energy it takes to get from where I start to the height of that peak. Okay, that's my activation energy. The other thing they've asked me about is the energy of the activated complex. The activated complex occurs right here. And so the energy that we're talking about for that species here is 250 kilojoules. So it's where it hits on that axis. All right. Let's try this again. So heat of reaction for this second one, we're talking about the difference here to here. And that's the heat of reaction. When we talk about the activation energy, that's the difference here to here. We call that EA, so that's the activation energy. And the energy of the activated complex, here, that number is approximately 100 kilojoules. So the energy at that peak, okay? So those are things that I might ask you to label here, or I might have something that has some arrows drawn on it and say, okay, which one of these arrows is the heat of the reaction? Which one of these arrows is the activation energy? Which one of these spots is the energy of the activated complex? Okay, and of course the energy of the activated complex is actually from here all the way down. Okay, so that's important. So it's not an energy difference. It is an actual absolute measure of energy. Okay? So that's some of the practice that we can look at there. Now, try this one more time. Here's some other ways that I might be talking about this. So what is the difference here? Heat of reaction. Where are we going to see that? Okay. Where would you see that? Is it any of these lines? Nope. It's the difference between A and D. So if I were to find the heat of reaction, it's equal to A minus D. Okay, so the difference between those two. The activation energy is B. And the energy of the activated complex, C, energy, activated complex. So transition state, activated complex, trying to think what else. There's a bunch of different titles that we use for that. All of them apply to that thing that exists, that transition state in the middle. Okay. Now, I'll talk about this again on the other side. So when we talk about the heat of reaction, we're still talking about the difference between A minus D, but of course, in this case, that's going to be negative, right? And we still want to do it that way. So we want to know that since that's a negative, we have to put that in, okay? So we always do it as A minus D. We still have the activation energy as, no, my activation energy here is C. So difference between our starting point and our difference between our starting point and that highest point. So sorry, thinking. This is also equal to C. What have they done? Sorry, trying to figure out what they've done. B minus A. Yeah, my activation energy there would be the B minus A, because that's the one that gives me that gap between the B and the top. Okay. And then if we want to talk about the energy of the activated complex, we actually don't have anything listed there. Oh, yes, we do. It's B. So that's that one. Okay. Sorry. Took a minute. So questions about that. So you might see any number of these things, and they may be labeled in such a way they have to do some figuring out and funking with them to figure out which one is the one that you're looking for. Okay? Well, that was fun. Questions, comments, problems at this point. Give me just a second. I want to see what the next bit is. Okay. Let's talk about these sample questions. So two reactions are being attempted at the same temperature. One has an EA of 77,000 joules per mole, and the other is 24,326 joules per mole. Under these conditions, which reaction is more favorable, first or the second? And when I mean favorable, I mean which gives me more product. I would say the second one. And the reason that I say the second one is because it's the lower energy, so it's going to be easier to hit that boundary, okay? And what is EA? So EA is the activation energy, so it's the difference between where I start and where I'm going to hit that transition state, so the highest energy point on that graph, okay? So that's EA. Now, examine the diagram. Which picture shows a reaction where heat is a reactant? So I have to add heat to make this happen. That's the second one. So this is heat plus heat. This is minus heat because it gives off the heat as a product. The temperature of the reaction is halved. Will the reaction be more or less favorable? So if I cut the temperature in half, what's going to happen? More or less favorable? I would say less, because temperature is a dependence. We need to have more energy to be able to get this to go. So if this happens, I would say less favorable. Circle it and underline it and make sure whoever's grading it knows that that's what I'm looking for. Two molecules collide with energy greater than EA. Okay. Are you going to get a product? Why or why not? No, they hit. They hit with enough energy to do something. Am I going to make a product? And my answer is maybe. And that's because if they're going to hit and make a product, they have to be in the correct orientation. And I have no guarantee that they're in that correct orientation. So my answer is maybe. I don't have enough information to tell you for sure. Next question. The kinetic molecular theory of gases assumes ideal behavior, where gases act as described previously. So we talked about this. Are real gases ideal? Are they? So I'm asking the question. Generally, that indicates that there is an answer. That answer usually is, probably not. and of course it does say ideal in parentheses or in parenthetically, which means that it's not real. So when two things collide, they do not just bounce off of each other with no transfer of energy. It doesn't happen. And so we know that they're not ideal. There are conditions where we can make them more ideal, to where they react more like the ideal behavior that we're looking for. But that's not always the case. And so we don't always see exactly what we expect out of the kinetic molecular theory because they're not ideal. Okay? So hopefully that's good. Questions, comments, problems, concerns, anything. Let me know. Let's talk if you're having issues. All right. Now, I'm going to stop here. And am I going to stop here? Hold on. Flipping. Okay. I'm gonna do the next couple slides and then we'll take a break when we get to the factors of effect. So, following reaction rates. Okay. So the rate of a reaction is measured using concentration of reactant or a product over time. We said that it's changing concentration over change in time. In this particular reaction, we're looking at the concentration of C4H9Cl, right? And the average rate is calculated by the change in C4H9Cl divided by the change in time. Okay, so if we go from the 0.1 to 0, that means that our change in concentration is 0.1. The time that it takes to get between those two is the 10,000. And so that gives me a rate that for that whole time period of 1 times 10 minus 5. For that whole time period. Okay. The table shows the average rate for a variety of time intervals. Notice that we can measure this between 2 points and get a rate for that. We could measure it between 3 points and get a rate for that. So we can do it at any point that we have data for. Okay, that's great. Awesome. I can measure it all over the place. But if I can measure it all over the place, how do I know that it's going to be the same thing that's being measured somewhere else? And that's where things start to get a little different. Okay. One of the things that we do is to plot the rate data. So we can plot that data, so concentration versus time, and it gives us more information about the rate. We can look at the instantaneous rate at time equals 0. So notice that we've drawn a straight line from that point. The slope of that line gives us the instantaneous rate. Okay, I said we'd come back to that. The instantaneous rate at time 0 is called the initial rate. So I can measure this slope anywhere. So the instantaneous rate at time t equals 600 is this one right here. Okay, it's often rate of interest at the beginning, the initial rate that we're really concerned about. So we usually measure that. I mean, we do measure that as we go. This figure shows instantaneous and initial rate of the earlier example. Reactions typically slow down over time, and that should make sense to you because as I have less and less and less of that reactant, then it's going to be harder and harder and harder for them to hit each other. So less product is going to be formed because of that. Okay, that's where we start getting into this equilibrium position because we have things that come apart and go together at the same rates, and it's not one of these individual cases. Okay, so wherever this flattens out to be, that concentration where it flattens out is going to be our equilibrium concentration. Okay, so that's a plot of our rate data. Now, what's an instantaneous rate again? All right, well, instantaneous is the slope of the tangent to the curve at that time. And so we'll measure all different ones for different points. And the average rate is the change in concentration over the change in time. And this could be for any time period. My initial rate is the instant slope of the tangent to the curve at t equals 0. So my time equals 0. Cool. I can define those things. And you might be asked, what else can we talk about? Well, here. As I said, rates are followed using a reactant and a product. And does that give the same rate for each reactant and product? No, it doesn't. Rate's dependent on stoichiometry. Okay, so if I have something that I need 2 of versus something I need 1 of, I'm going to consume the one that I need 2 of twice as fast. So we need to be able to look at that. If we followed the C4H9Cl and compared it to the production of the C4H9OH, the values would be the same. So we do this for the C4H9Cl, which is my reactant. It's negative, and it's equal to the rate of production of C4H9OH. So the change would have opposite signs. So one goes down, and again, we make that negative for the reactant so that we can do comparison between reactant and product. Okay, so that's cool. So we can look at it from that. But if your equation is not 1-to-1, then we have to deal with that. Okay, so what would be the relative rates for 2O3 compared to 3O2? Well, if I were to measure the O3, that would be different than the O2 in terms of sign. So we have to put the negative sign out in front of the O3 to make it equal to the O2. But the other thing that I have to deal with is the fact that I need 2 O3s to make 3 O2s. So that's a very different situation in terms of what those concentrations are going to be. And so what we do is to take our rate over that time period and divide it by the stoichiometry. So if we multiply by 1 over that stoichiometry, it corrects for the stoichiometry. So we should be measuring the same thing from any place. And that's what we call a relative rate. Okay. So K equals rate over the concentration of Br2. Average rate is proportional to the rate constant. So if I take my average rate, K is equal to that rate over the concentration of Br2. A plot of the rate versus concentration will give you K. It's the slope of the line that we'll get, and we'll talk about this again. For gases, you can use the following equation to look at the rate by measuring the change in pressure according to the following equation. So just like we had the ability to convert from Kc to Kp when we did that, we now have a correction to get from concentrations to pressures, and that's 1 over RT. So we have to put that in front to make sure that we've done a correction for the pressures between pressure and concentration. Okay, so hopefully that's cool. All right, awesome. This is so much fun. A few examples. Consider a Haber process. 2NH3 goes to N2 plus 3H2. I can calculate the rate in a number of ways. So delta H2 over T, delta NH3 over T, delta N2 over T. But if I do that, while that does describe the rate of the reaction, it's relative to that species. So if I want something that can be compared, we need to correct for the stoichiometry. So the rate for NH3, if we didn't correct, would look larger than the one for N2 because I need 2 NH3s and I'm only talking about 1 N2. Okay, so in order to make them all the same, we have to consider the concentration goes up or down and the stoichiometry of it changes. So it's going to be a negative 1 over 2 times the concentration of NH3 because it's a reactant. Okay, we divide by its stoichiometry. And that's equal to the rate of formation of N2 divided by T, because that stoichiometry is 1, and that's equal to 1/3 of the concentration of H2 over delta T. Okay, those rates should all be the same because they've been corrected for the stoichiometry that we're dealing with. All right. Okay, so let's consider the following equations. I want you to write average rate expressions for each species in the equation. Okay. So I have 2 NaNO3, so we would start with the concentration of NaNO3 because it's changing concentration over the change in time. But remember that this is a reactant, so it's going to be negative, and it's 1/2 because that's the stoichiometry that I have there. That's equal to concentration of PbO, change in that, over the change in temperature. And that's equal to, and this one is negative as well, sorry, that's equal to the change in concentration of the PbNO3 2 over delta T. That's also equal to concentration of Na2O over delta T. Okay. So we've corrected on a number of fronts. One, reactant versus product, and the other, stoichiometry. Okay, so the one that had the number out in front of it, we've divided by that number. Okay, let's talk about our 6AgI plus Fe2CO3 goes to 2FeI plus 3Ag2CO3. Okay, change in concentration, AgI, over the change in time. And it's going to be negative because it's reactant, and 1/6 because there were 6 of them. That's going to be equal to the negative of the change in concentration of Fe2CO3, 3, or the change in time. And we don't have to do any stoichiometry with that because it's 1. Okay. Let's look at our next one. So it's a 2 FeI3, so it's 1/2. It's positive because it's a product. And so we're looking at the change in FeI3 over the change in time. And that's equal to 1/3 times the change in concentration of Ag2CO3. And I forgot my change, so it's delta over delta T. Okay, so that's for that one. I'm going to move my C2H4O2 down here. So I see that that is a 1 in front of it. So it's negative because it's a reactant. Change in concentration of C2H4O2 over the change in time. That's equal to negative 1/2, because it's a reactant again, change concentration O2 over delta T. That's equal to 1/2 times the change in concentration of CO2 over the change in time. And that's equal to 1/2 times the change in concentration of H2O over the change in time. Okay? Ooh, that's so much fun. Now, these 3 right here, I want you guys to think about. And again, I'm going to put those answers on D2L, but I want you to look at this and see what is the pattern that we've done here. How is this being accomplished, handled at this level? Okay? Questions, comments, problems? All right, I hope not. I'm going to take a break here, stop this recording, and I will be back with you soon.